Although we know that computer technology continues to rapidly advance, sometimes our software feels like a bit of a regression. Today we'll talk about why sometimes software feels slower even though our hardware continues to get faster and faster. Welcome to Kopec Explains Software, the podcast where we make computing intelligible.
All right, Dave. So the short answer to is software getting faster is yes, but that's because hardware is getting faster.
Absolutely. Of course, software runs on hardware, and hardware continues to improve by leaps and bounds. There's something known as Moore's Law. It was coined by somebody named Gordon Moore, who was a CEO of Intel and an innovator himself way back in the day. It's been going on for decades now, and it basically says that we expect every 2 years the number of transistors that can fit on the same size die to approximately double. And when we have more transistors, we can do more in hardware. And for a long time, what we were able to do in hardware was we were able to make our microprocessors faster and faster and faster by raising their clock speed, which is what you know as gigahertz. As you might have noticed, we hit kind of a wall in terms of gigahertz about 10, 15 years ago. And what we're getting instead now, and we're using those extra transistors for, is more and more what we call cores on the microprocessor. You can think about it as before about 2005, consumer microprocessors had one brain. Now a modern microprocessor has multiple brains. And so while each of those brains on their own might not be that much faster, they are still getting individually a little bit faster. Having many of them means we can divide up our tasks amongst them and have all of them working together to complete the tasks. However, even though we're getting more and more brains, more and more cores on our microprocessors, what we need to do also in software is support those additional cores. Because a lot of software back in the day was designed thinking there's only one brain, there's only one core. Now today, what software developers need to do is make their software parallelizable, make it possible for its tasks to be split up and run on all of those different cores at the same time. So that's been a shift that software developers have had to make to take advantage of this better hardware that we're getting. And for the most part, they've done that. So we do today have highly parallelizable software. If you take something like your modern web browser, your modern Office suite, it's going to be taking advantage of all of those different cores that you have in your modern microprocessor. So, but absolutely, hardware continues to advance rapidly. And of course, as a result, our software is getting faster and faster by being able to take advantage of that hardware.
When we talk about software getting faster and faster, I feel like we should dissect a little bit about what we mean by faster. Like, is it faster to just start up or faster to complete a task?
Right, how do we actually measure speed? There's a few different ways. Number one is we might just look at benchmarks. Benchmarks are synthetic benchmarks usually, meaning that they're not based on real-world tasks that a user might do. They're based on trying to stress the microprocessor. A couple benchmark apps that some of our listeners might have heard of are Geekbench and Cinebench. They're good at really telling you, well, this microprocessor seems a bit faster than this microprocessor. But what they're measuring are very, very synthetic items. They're not like spell checking in Microsoft Word, or how fast does this web page take to render. For those kind of benchmarks, those more real-world benchmarks, we sometimes look to the media. Sometimes computer publications will do actual examinations of how long real-world tasks take to complete. To give you a really illustrative example of measuring real-world tasks, one thing I loved in the late 90s, early 00s was when Steve Jobs would give his Macworld keynotes, he'd take a state-of-the-art Mac, a state-of-the-art PC, and do what he called a bake-off. A lot of Mac users at the time were graphic designers, so he'd take Photoshop on both machines, have it run with a script that would do a bunch of preset actions, and see which machine would complete first, the Mac or the PC. That's a pretty good example of measuring real-world performance. But for us as regular users who are not maybe graphics mavens, we're actually more thinking about how does the machine feel? Have you ever heard somebody say to you like, oh, my new machine, it actually feels like slower than my machine from 5 to 10 years ago. And you wonder, how can they think that? Well, there is actually an explanation for that. You're not always doing an apples to apples comparison. Maybe on your new machine or what you're doing now on your machine is using quite a different type of app than you were using 5 to 10 years ago. It might even be in the same genre of apps. You might, for example, be using a word processor like Google Docs. And 10 years ago, you were using Microsoft Word. Now, Google Docs is a web application. It runs within a web browser. Microsoft Word is a native application. It runs directly on your microprocessor without all these layers of abstraction between it and the hardware. And so you're not really making an apples to apples comparison. If you say, my new computer feels slow and you're doing all your word processing in Google Docs compared to your old computer where you were always using Microsoft Word. So we need to really be thinking about, when we're talking about performance, are we making an apples to apples comparison?
Is part of why software might feel slower or be slower also the programming languages and the programming environments that software developers are using now?
Absolutely. We've talked in the past on this show about different types of programming languages. If you were writing software in the 70s or the 80s, you'd be using a very low-level programming language. You might even be using assembly language, which is very close to the metal, or you might be using C or Pascal, which are relatively low-level programming languages. And they have less layers of abstraction between the programmer and the hardware. And they are just inherently going to be faster languages when programs are executed than a modern language like the most popular languages today, such as Java and Python, that are several layers of abstraction above the hardware. You take the same exact program and you write it in assembly language, and then you write it again in Python, and it's going to be many times slower in Python than it is in assembly language. So if you take the same exact hardware and you take one version of the program written in assembly language, one version written in Python, you're going to notice quite a difference. Now, the vast majority of applications today are built in high-level languages. They're not being built in low-level languages. That alone is incurring a performance penalty. So there's a reason why some software running on much more primitive hardware felt much faster for certain tasks than modern hardware running equivalent software written in a much higher level language.
Will software developers use these languages that are closer to the metal for specific types of tasks or programs that they're creating?
Absolutely. They still do that all the time. So there's ways from modern high-level languages of interfacing with libraries or pieces of software that you built in a low-level language. So it happens all the time that people program in Python and they use what are called C extensions, which are little pieces of software written in C for performance reasons that the Python software interacts with. So absolutely, we still do that kind of optimization all the time. But if the vast majority of our software is being built in these higher-level languages, there's going to be a performance penalty incurred.
It's a trade-off.
It's a trade-off. And these higher-level languages are more developer-friendly. They allow developers to produce their applications in a shorter period of time, or they offer more safety features to ensure that programs don't crash. So they actually are a boon for our developers, making our developers more productive. And that's why we don't write everything in these low-level languages, even though they're more performant.
Even though our hardware is getting faster and as a result, software is getting faster, there actually are some things that have slowed down a little bit or were faster back in the day, back in the 80s.
One really interesting example of things that were actually faster in the past was discovered by a fellow named Dan Liu, who did a little experiment looking at what's called keyboard latency. And I'm going to put a link to his blog post in our show notes. What Dan looked at is if we have a keyboard and we press one of the keys on the keyboard, how long does it take for the image of that character to show up on the screen using like a standard terminal program? So what did he do? He actually took a high-speed camera and recorded it, and then he played back the film and was able to look at, well, this is exactly how long it took. So it wasn't some synthetic benchmark. It was very, very real. Interesting thing he found, going way back into the 1980s on an Apple IIe, it took 30 milliseconds for pressing a key on the keyboard to show up as a character on the screen. 30 milliseconds, that's 30 thousandths of a second. Whereas he looked at something like a modern PC running Windows in 2017 when he did this experiment, and it could take as long as 200 milliseconds. That's almost 10 times longer to have that press of the key on the keyboard show up on the screen. Now, there's many different things that are being measured there. Of course, there's hardware being measured. How long does it take for the electrical signal from your keyboard to actually get processed by the microprocessor? Okay, there's some software in between though. There's software of what's called interrupts. Interrupts are things that happen when a hardware device happens and it interrupts the machine and says, hey, something happened on this hardware device, you need to deal with it. There's software parts to this. How long does it take the program that actually gets the keyboard events to process the keyboard events and display a character on the screen? There's parts of the operating system's rendering engine, the part that probably handles text of the operating system, and how performant is that. So there's many different layers of software and hardware here that go into this. But the bottom line is, actually in this benchmark, yes, a machine in the 80s was faster than a modern machine. And I think a big part of that is how little abstraction there was on those machines in the early 80s. There weren't that many layers of software between seeing that character and the actual hardware that produced the character.
I guess I'll deal with my keyboard being a little bit slower for all the modern features of my computer today.
Yeah, of course our machines today have so many more features than a machine did in the late 70s or the early 80s. That's not to say, though, that there isn't software bloat. We have these much more advanced programming languages. We also have many more layers of abstraction. I want to go back to the Google Docs example, because when you run Google Docs versus running Microsoft Word, it's a very, very different software stack that's processing all of your work in the program. So let me talk to you a little bit about what it's like. So Google Docs is running as a JavaScript app in your web browser. Your web browser has a JavaScript interpreter or just-in-time compiler that's taking the code in Google Docs and converting it into machine code. So it's actually that extra layer of abstraction. The web browser is providing another layer between it and the operating system, which is then actually sending that over to the microprocessor, of course. And then there's also the fact that Google Docs is loading a lot of its features off of a server and continually saving your doc live in the cloud. So there's some latency that's inherent in that as well. Every time we use Google Docs, we're constantly connected to Google servers, sending data back and forth. Now contrast all of that with Microsoft Word. When you run Microsoft Word, which is a huge app, of course, with many more features than Google Docs, but it's running as a native app. It's running directly on the operating system, not with that extra layer of the web browser between it and the operating system. It's also running and built in faster on average programming language. I think a lot of Microsoft Word is implemented in C++ to my knowledge, which is a lower level programming language than JavaScript and inherently more performant. And Microsoft Word, most of its features are running locally on your machine. It's not having to send data across the network up to Microsoft servers and back for everything that you do, although it does have some features that utilize the cloud as well. So for all of these reasons, Microsoft Word on average is inherently going to be more performant than Google Docs. And so when we say, oh, my computer feels like pretty slow compared to how my computer felt 10, 20 years ago, if you were running Google Docs on a computer 10 or 20 years ago, it would feel super slow, right? So we have to really be making apples to apples comparisons when we say, oh, something feels slower. In general, our hardware has gotten tens, thousands, even if you measure some things millions of times faster over the last few decades. Our software has not gotten millions of times faster because we've added these extra layers of abstraction and because there are some inherent limits in some things that are algorithmic to how fast we can do them. But the bottom line is, yes, our software is getting faster if we actually look at an apples to apples comparison, but because we keep adding more and more layers of abstraction to the software that we use, it feels sometimes like it's getting slower. All right, thanks for listening to us this week. Rebecca, how can people get in touch with us on Twitter?
We're at Kopec Explains, KOPECEXPLAINS.
Don't forget to subscribe to us or follow us on your podcast player of choice, and we'll see you next week.
Bye.